Optimal multi-user resource allocation of cloud LAN in 5G using machine learning. Abstract. The networks are evolving drastically since the last few years in order to meet user requirements. For example, the 5G is offering most of the available spectrum under one umbrella. In this work, we will address the resource allocation problem in 5G networks. To be exact, in the cloud radio access networks (CRAN), the radio access network (RAN) mechanisms involve multiple network topologies that are isolated based on the spectrum band, and it should be enhanced with numerous access technology in the development of 5G networks. CRAN is one of the optimal techniques to combine all the available spectral bands. However, existing CRAN mechanisms lack the intelligence perspective on choosing the spectral band. Thus, CRAN mechanism requires an advanced tool to identify network topology to allocate the network resources for substantial traffic volumes. Therefore, there is a need to propose a framework that handles spectral resources based on user requirement and the network behavior. In this work, we introduced a new CRAN architecture modified as multi-tier HCRAN in 5G environment. This architecture handles spectral resources efficiently based on the simulation analysis. The proposed multi-tier HCRAN architecture with improved CU networks managed perspective enables augmented granularity, end-to-end optimization, and guaranteed quality of service QoS by 50% over the existing system. Keyword: net regular access network, quality of service, baseband unit, quality of experience. Introduction. In the midst of this data revolution era, the evolutions in the network's generations should be steered largely to hold a faster data-oriented service that can be fulfilled in 5G. The forthcoming networks is planned to evolve based on the user expectation and demand, which in turn form the basement for the 5G network's goals. Some of the predominant targets of 5G are low latency, high bandwidth utilization, and interoperability. To achieve the significant goals of 5G, efficient network management and compatible network architecture is required. The 5G networks incorporate various emerging technologies like software-defined network (SDN), network function virtualization (NFV), and mobile edge computing (MEC), which were proposed by the main working group of 5G networks like NGMN and 3GPP. The 5G consortium has planned to utilize the available spectrum of all the communication and data sharing bands of the licensed spectrum such as LTE, UMTS, and unlicensed spectrum like Wi-Fi. The advanced antennas with multiple input and multiple output MIMO technologies can be adopted in the evolving 5G to provide higher data rate 3 and 4. The closer requirement of future 5G networks cannot be accomplished by the existing radio access networks (LAN), wherein the baseband units (BBU) and the radio units (RU) are consolidated. Meanwhile, the cloud-enabled service in 5G ecosystem cater heterogeneous communication framework utilize advanced virtualization techniques. The network virtualization stimulates multi-service and multi-latency for efficient network operation and service provisions, which in turn offers new flagrant service-oriented and edge cloud 5G architectures. With enhanced quality of experience (QoS), thus the current LAN architecture needs to be further extended with various virtualization techniques to develop cloud LAN, CLAN abutment, the correlation of access point (AP) to the pool of BBU via a tube of transport links in the control unit (CU), which conquer the limitations in the traditional LAN. However, CLAN requires an intelligent technique to recognize the topology of the networks in the mobility stage and to locate the resources as a vast traffic volume created by the sampled radio signals are directly transported to the CU. The next generation networks are expected to run consistently based on the various user behavior and spectral stability that depends on both the user's environment and network's behavior. Thereby, seamless service can be ensured for the nearly as per the requirement by predicting the most advantageous networks that can render service. The chosen optimal networks will offer seamless service with highly sophisticated running and decision making through machine learning techniques. Machine learning is the most robust artificial intelligence domain which comprises of assured techniques for improving the operation and management of new networks and engineering applications in the future cellular networks. The machine learning algorithms employed for mobile networks can endeavor plentiful opportunities to solve the advanced threat and enhance connectivity. Hence, the machine learning aids CLN architectures are expected to perform as an intelligent radio propagation medium which can automatically access the available spectrum and can regulate the power to be transmitted in the interest of energy conservation. It is believed that an innovative CLN with machine learning techniques form a new designed prototype in the 5G networks architecture which will most probably introduce considerable modifications in the air interface and the tensile network management. Thus, Sheeran invites a fruitful solution that solves the issue of interoperability by utilizing various spectrum bands by running the dynamic changes in the networking paradigm. In this article, we proposed a multi-tier HCRN in 5G by adopting the machine learning techniques to address the current limitations of huge traffic in the BBU pool of existing architecture. The proposed architecture is also improved to facilitate augmented granularity, end-to-end optimization, and guaranteed quality of service. This article is organized as Section 2 discuss the literature on the recent research solution that contributes to the domain of 5G machine learning. The feasibility in the physical deployment of LAN in heterogeneous networks is explained in Section 3. In Section 4, proposed multi-tier HCLAN architecture with the running tier is briefed. The performance of the proposed system is analyzed in Section 5 under various assumptions and 5 scenarios. Finally, Section 6 concludes the article with the interference of analysis made on the proposed system. Second, related works. The 5G networks is evolving to satisfy the end-user requirements such as seamless connectivity even with high mobility, low latency, and interoperable connectivity. The Mobile Communication Working Group and a consortiums focus on providing new spectrum band, on improving spectral efficiency and throughput when considering the business models related to coverage and reliable broadband access. To meet the user requirement, LAN is redesigned to scale the parameters such as throughput many devices and connections concerning user plane, UP, and control plane. The evolving 5G LAN architecture support mechanisms that relate to traffic to fulfill quality of service and to control T2D connectivity. LAN technology also assists in reducing the traffic services and enables network slicing. However, there is a possibility for LAN to be designed up with heterogeneous networks like Wi-Fi and LTE small cells, i.e. HetNets. By the recent advancement in the cloud computing paradigm, the integration of cloud technology with the LAN named CLAN is believed to be a productive solution to solve the heterogeneous interoperable problems. CLAN is the most promising design for the mobile network system to provide scalable and smooth traffic transmission. CLAN integrated with HetNet has achieved a flexible and reconfigurable dense deployment of small cells. CRAN holds the potential in giving efficient, effective communication and information exchange among the terminals. When CRAN is modeled with the assistance of SDN, it gives a space to configure and manage the dense small cells deployment 16 and 17. To enhance the QoS in CRAN, BBU pool is relocated into BBU and remote radio head RRH, where BBU is enabled with the central processing unit to provide networks coordination and management. BBU helps in reducing the traffic when deploying the small cells, i.e. hatchnets with containing thousands of small cells. In BBU, there is possibility of several other challenges like effective radio resource management, spectrum, and energy efficiency network to enable QoE, resource management in small cells and multi-hop networks. By considering cooperative radio resource management, a modified CRAN framework has been proposed to provide an improved indulgence of resource allocation. It also enables flexible resource management with improved QoS parameters such as throughput and fairness. 18. The modified CRAN frameworks allow flexible resource management, i.e. the amount of resource used for the end users is made dynamic. Several issues came into existence when CRAN is combined with HETNet, such as coordinated multi-point transmission and reception, resource management in self-organized networks, and improved spectrum utilization with energy estimation in several systems. In CRAN, the transmission demand BBU and RRH are considered for the differentiation of service and RRH demand in transmission links, i.e. black hole is improved by balancing the workload, which is labeled as multi-point transmission. 19. In CRAN, BBU and radio access units (RAU) are also isolated to provide centralized processing, then reduce operation expenses, while mapping RRH and RAU in heterogeneous networks. The hardness of configuration and energy efficiency are the prime parameters to be considered. CRAN along the orthogonal frequency division multiple access OFDMA techniques helps to map BBU and RAU for providing reconfigurable black hole transmission and effective energy utilization. Efficiency pre-coding scheme has been designed for the environment like CRAN with the full field channels metrics using beamforming, i.e. zero forcing to reduce energy consumption and computational complexity, incorporation transmission, centralized processing of thousands of small cells helps to perform multiple cell joint scheduling, but interference problem and frequency reuse play a significant role in the dense scenarios. 22. Next generation networks are often planned for the improved data rate, which is used for many essential applications like sensing, resource management, etc. Challenges faced by radio technology has to provide creative learning and decision-making platform for efficient frequency planning. Based on radio frequency spectrum, a heterogeneous network meets spectral inefficiency, interference, transmission, and power inefficiency. Concerning QoS and 24, HETNet face the problem of inefficient radio resource management and optimization for the user satisfaction. 25. To overcome the various networks graduation problems, artificial intelligence techniques such as machine learning, fuzzy neural networks, etc. play an important role to provide practical solutions. When artificial intelligence deployed on the CRAN by integrating HETNet, base stations (BS) use dedication of black hole to provide guaranteed black hole and small cells deployment offers seamless connectivity to offload the data in traffic. If CRAN is automated or made intelligent, then RRH black hole connection of RLAN can be combined with a BBU pool to create a centralized processing unit. 27. Due to the tremendous traffic generated by mobile users, The future mobile networks deployment is going to be extremely complex. The spectrum utilization in the densely populated networks in a challenging task, and if machine learning 28 is used as an optimization tool to optimize the CLAN, the resource allocation scheme will be enabled to downlink HCLAN 29. HCLAN aims the reduction of an interference problem to maximize the energy efficiency and guarantee the QoS between RRH and all UE present in the networks. In this paper, we propose a multi-tier HCR architecture that can provide seamless connectivity by monitoring the network's conditions and user behavior based on the behavior pattern to available the required technology in the future. Also, the proposed multi-tier HCR considers the problem of interference to get optimized resource allocation further to improve the QoS. 3. Third, deployment of LAN in HETNET. The key of our proposal is to deploy LAN in the scenario of HETNET in order to buckle with the scope of small cells prosperity. Cloud radio access networks CLAN with minimized capital expenditure, CAPEX, and operating expenditure OPEX is proposed. CLAN have independent baseband units BBU and independent RAUs. These standalone units are migrated from centralized processing and are placed in the cloud. The backhaul that connects the BBU and RAU is said to be principal component of CLAN. For efficient network management, the 5G leverages SDN, NFF, and mobile edge computing principles. The large requirement of future 5G networks cannot be accomplished by the existing radio access networks RAN, wherein the baseband unit BBU and the radio units RU are considered. Cloud RAN implement the correlation of access point AP to the pool of BBU via a troop of transport links in the control unit CU, which conquered a limitation in the traditional LAN. However, CLAN requires intelligent techniques to recognize the topology of the networks in the mobility stage and to locate the resources. As a vast traffic volume created by the sampled radio signals are directly transported to the CU. Initially, machine communication services are categorized as massive machine-type communications (MMTC), enhanced mobile broadband (eMMBB), and ultra-reliable, low-latency communications (URLC) services. 13, which have very different performance requirements and traffic profiles. Thus, the listeners and extensibility introduced by the new CLAN architecture grant to deviated the vision from the generic CLAN and to multi-user CLAN. In the multi-layer CLAN, UE assignment should be dealt with adequate dormancy to solve the UE latency and energy utilization problem in RRH. Thus, we propose a novel architecture involving multi-layer of CLAN networks as a multi-tier HCLANs. The proposed architecture is also equipped with unique control and innovative management schemes to effectuate augmented granularity, end-to-end optimization, and guaranteed quality of service (QoS). To support these new cases in this work, we inherit machine learning paradigm with CLAN deployment for high scalability and flexibility. So the next generation architecture extends the cloud LAN technology to ultra-dense networks that incorporate macro, micro, and small cells in diverse spectrum bands, i.e. HETNET. 3.1 Generation of HETNET. HETNET incorporates the bulk quality of compactly deployed small cells such as femtocells, picocells, relay node, LTE and Wi-Fi access point, and the small cell can serve both as indoor or outdoor UEs. These are deployment in the densely colonized region to reconcile the immense traffic cravings. picocells maneuver on licensed band and use either optical fiber or microwave interface as backhaul to get connected with the core networks. They are set up by the cellular speculator is either in an organized or in an unorganized way. At numerous traffic hotspots, femtocells are habitually functioning on licensed bands and exploit the broadband internet linkage as backhaul. The core network is then linked employing either extended digital subscriber line, DSL, or cable modem, one of the done with the IP networks. They are incorporated by human beings predominantly on the way to deliver interior coverage. Relay node RN is a stretched version of the benefactor evolved node B, E, and B. It is linked with the benefactor E and B through the mediator U amalgamator in addition to the radio link. Backhaul is capable of exploit either clonal frequency band in band as being pre-owned in air mediator or capable of exploiting peculiar band outband. U is coupled with RN through the mediator. When an UE does not become familiar with the case, it is associated to rely on networks, then the relay will be translucent, or else when the UE is familiar with the case, it is associated to network or relay. The relay will be non-translucent. Wi-Fi AP are small cells habitually functioning on licensed ISM band and with a frequency between 2.4 GHz and 5 GHz. Wi-Fi AP are incorporated either by a manipulator or human beings to afford a cramped coverage zone and can be positioned indiscriminately in the interior of every cell, which has the capacity of transmitting power varies from 100 milliwatt to 200 milliwatt. It makes use of the broadband internet connection as backhaul. LTE small cells are endorsed because of the organization listness, curtailed capital, and optimal operational cost, in addition to the diminishing energy regime. As a result of the supplementary compressed arrangement of feature, the LTE network is alienated into the two parts. The LTE part has radio access expertise, while the evolved packet core EPC handles the expertise allies to our core networks. A UE fixed to an E-node by means of radio mediator. The E-node executes the administration of radio resource tasks such as allotting radio resources in addition to the administration of inter-cell interference. The general network architecture differentiating HANET, SHRAN and HSHRAN is depicted in Figure 1. By scheduling transmission centrally, SHRAN can improve cells edging performance by the addition of reducing the interference and can serve the user across different radio access barriers, which intercede connectivity and decoupled uplink and downlink. Cloudline introduced the concept of the no-edge networks to ensure consistency improve user experience in high-density networks. The central controller of the SHRAN can be designed using cloud-native software to run on general-purpose telco cloud infrastructure. The placement of the controller corresponds to an edge data center facility that is capable of running multi-access edge computing MAC service. One opportunity is to consider how the radio access and the cloud-based MAC services can be integrated. For instance, to enable developers and content providers to optimize their services according to the desired or available radio bandwidth. It is expected to be useful for ultra-low latency and mission critical services in 5G and each being formalized with the CU and DU functional split. On the DU side, for example, the use of massive MIMO associated with beam trafficking and beam switching techniques require highly accurate time estimation to support mobility, which point toward distributed real-time radio functions, as optimal artificial intelligence techniques are believed to be an optimization tool to optimize the CLAN in the network.